Thanks for attending my session at KansasFest 2020. I'm Joe Strohsnyder, and this is Trick Out Your Transparent Apple, NeoPixels, Arduinos, and Gameports. Oh my! I'm an IT professional from Central Ohio. Windows PCs, hardware, and networks are my trade, but retro computers are my passion. I've been into computers since basically forever, and it goes without saying that the Apple II is my favorite. I have a YouTube channel called Joe's Computer Museum where I review, repair, and restore old 8-bit systems, so check it out if you haven't seen it already. So what is this session about? Well, with Mark Joseta's transparent Apple IIe case coming soon, I figured folks would want to trick it out with lights. Now, anyone can just put blinky lights in there, but I wanted to see if we could make the Apple II control those lights. In this session, we'll go over how to control a 60 LED NeoPixel strip with an Apple IIe using the Gameport for control and an Arduino as a translator. I'll discuss how NeoPixels work, timing, power, and wiring plans, Arduino code, and finally controlling the system with Applesoft. All of the code and wiring information are available from download from my website at jcm-1.com/NeoPixel. Now, it's important to note that I'm not the first person to do this sort of thing. I came up with the idea independently and only realized it had been done before during my research. However, as far as I know, I'm the first to design a working system that allows the Apple II to control the 800 kHz NeoPixel system directly from Applesoft. With that said, let's get into it. So what is a NeoPixel? NeoPixels are individually addressable RGB light-emitting diodes that are controlled over a single serial wire. They are found in either strips of LEDs or LED matrix panels. Basically, you just give the strip some power and feed it the right commands into the serial data line, and you can individually set the color of any pixel in the strip. When I first saw the transparent Apple IIe case, I immediately thought of an Apple II controlled NeoPixel strip. I figured it'd be pretty easy. Just hook the strip into the Apple power rails, pipe one of the Gameport annunciator outputs to the serial data line, throw some assembly code at it, and we'd be in business. But it turns out it's not quite that straightforward. The NeoPixel strip is controlled by serial commands sent down that control wire. The signaling rate is 800 kHz, and the duty cycle of the signal is varied to tell the strip whether or not you're sending a 1 or a 0. As you can probably see, this is already a problem. The Apple II runs at 1 MHz, or 1023 kHz, approximately. If you know about Nyquist limits, you know that the best we could do is about 500 kHz. Even if we code the tightest unrolled loop possible, we can get about 100 kHz. Considering that we need duty cycles smaller than 50%, the actual signaling rate is higher than 800 kHz. The final consideration is ease of programming. NeoPixel can be easily controlled with the excellent pre-built control library made for Arduino controllers. Now, I could reinvent the wheel in 6502 assembly, but why, when there's already code out there that can do that? Combine all this, and you come to the conclusion that I did. Use the Apple II to control an Arduino, and use the Arduino to control the NeoPixel strip. So, how do we power these devices? At first, I thought we could just power them right off the Gameport, but that dream would be brutally smashed once I started looking into it in more detail. Here's the scoop. The Apple II spec says you can't draw more than 100 milliamps from the socket. Now, the Arduino is fine itself, it draws about 55 milliamps maximum. But a 60 LED NeoPixel strip at full brightness draws almost 2.1 amps by itself. Now, that's not only a problem for the socket, but also a problem for the Apple power supply. It can only supply 2.5 amps at 5 volts. So you'll either need a supply that can generate more juice, like the reactive mic or universal power supply, or an external unit. If you use the Apple II power supply, you'll want to build a Y connector to draw your power straight from the power supply. Trying to pull 2 amps through the board is not a good idea. It will turn your traces into resistive heating elements, and what you don't want to generate light will start glowing. How do we talk to the Arduino controller? I settled on using the 4 annunciator pins on the Gameport, with each pin having a dedicated function. These pins are wired to GPIO pins on the Arduino. Annunciator 0 goes to the Arduino's interrupt pin. We use this to get the Arduino's attention. Annunciator 1 goes to a clock pin. We use this to latch data sent to the Arduino on that data pin. Annunciator 2 is the data pin. We use this to actually send data bits to the Arduino. And Annunciator 3 is a special command signal. This lets us differentiate between a simple mode toggle and a full command request. The basic theory of operation is thus. If we toggle interrupt low to high while command is high, we are just signaling the Arduino to step to the next of one of the pre-built Apple color modes. If we toggle interrupt low to high while command is low, that means we want to send custom commands to the Arduino. While in this mode, command pulled low, we put data on the data pin and then toggle the clock pin low to high to latch in that data bit. We repeat that for all of the bits that we want to send to the Arduino. Once we are sending commands, we pull command back to high. This tells the Arduino we are done and to go parse and execute the command that we just sent. If you are using an Arduino Uno, a 1 meter long 60 LED NeoPixel strip, and my demo code, the basics to hook everything up are shown here. It is important to note that the Apple, Arduino, and NeoPixel grounds should all be tied together. This ensures that all of their data signals will be at the same reference. To power the NeoPixel strip, you can create a Y adapter for your Apple power supply. This is the cleanest and prettiest option, but requires an aftermarket power supply. I suggest using an external 5V 2.5 amp power brick instead. If you use the Gameport for other things, you'll want to consider creating a pass-through port by using a machine pin socket like pictured. Now let's dig into the code. I'll use pseudocode here for the non-programmers, so you can see how it works. If you like, you can download and read the actual code later at your leisure. We get interrupts on the Arduino by binding GPIO pin 2 to an interrupt handler. Inside that handler, we check the state of some things so we know what to do when an interrupt is triggered. Like all interrupt routines, it's kept as short as possible. When not responding to interrupts or fetching data, the Arduino sits in a nested loop executing the mode it was commanded to execute. It does that by acting on a global state variable. The built-in modes that it can execute are thus: display static Apple colors, chase Apple colors, fade Apple colors, twinkle Apple colors, chase custom colors, fade custom colors, or it can be in command mode, where it's receiving and parsing a specific command. Now about that command mode. When told to, the Arduino will listen for, parse, and execute a series of commands sent to it from the Apple II. Getting data from the Apple II works as thus. While the command pin is low, it sits and waits for the clock pin to go low. The moment the clock pin goes low, it will latch in whatever is on the data pin into an input array. It will then sit and wait for the clock pin to be low again. What this does is it allows it to latch that data in only once. As you can see by the way these while loops are nested, the moment the clock pin goes high, it bounces out of both those clock pin loops and goes back to the command loop, waiting for the command loop to be high. Once the Apple II has sent the command to the Arduino, the Apple II then sets the command pin high. The Arduino then knows it has to go parse and execute the command. Now let's talk about the commands that the Arduino is programmed to understand. The beginning of a command stream is a single byte that equals the total number of commands being sent to the Arduino. After that, each command value is a single byte, followed by a series of argument bytes depending on the command itself. The commands that the Arduino understands are thus: 0, meaning clear the strip to all black, or turn all the LEDs off. 1, which means fill a range of pixels to a single color. 2, which means set a specific pixel to a color. 3, which means run the chase animation on whatever is already on the strip in order to create a custom animation. 4, which means run the fade animation on whatever is already on the strip, again to create our own custom animation. 254, which means I want you to switch to one of the built-in Apple color modes, or 255, which means reset the system. As you can see, with these custom command modes, you can not only just tell the strip to show Apple colors, you can tell it to show whatever pattern you want, and then also animate it. Now let's take a look at controlling things from Applesoft. Since the Arduino can get commands at any speed, that means we can easily control it from Applesoft. That makes demonstration easier and debugging easier too, in my opinion, so let's take a look at that. Commands are sent as a string of bytes, but each byte is sent as individual bits from least to most significant in that byte. I find it easiest to create a string of command bytes, then loop through that string to parse and send each bit individually. As discussed, we make a command string by starting with a byte that equals the total number of commands in the string. So if we have 2 commands in the string, the first byte will be 02. We then send a command byte, followed by all of the command arguments. The string is easy to assemble in Applesoft using arrays and string operators. Sending the command works like this. We set the command pin low, we toggle the interrupt pin, like that, so the Arduino knows we're sending a command. We then loop through each byte in the command string, sending bit by bit. We set the data pin appropriate to that bit. We then turn the clock pin low, then high, and repeat until we've sent all the bits. Once we're done sending the bits, we pull the command pin back high. If we've done it correctly, the NeoPixel strip will now be showing whatever we told it to show. Well, enough talk. Let's look at some pretty blinky lights. Okay, before we get started, I want to just go over and review all of the wiring and connections of everything between the Arduino, the NeoPixel strip, and the Apple II so you can see it physically in reality as it's connected to the system. To start, here's the game connector. As you can see, I have it wired into a machine pin strip with the wires soldered on the back of that strip. That ribbon cable that I made winds its way down through there and over to the Arduino controller itself. Here are the power pins that come off of the Gameport that power the Arduino controller. Here are the annunciator pins that are used to send signals to the Arduino. These 2 wires here are the ground and signal pins for the NeoPixel strip itself, which kind of sneaks its way up and over into the connections there for the NeoPixel strip. And finally, this super thick cable right here is my external power for the NeoPixel strip, which for now I am powering from my bench power supply. So without further ado, let's get everything all started up, and for that we're going to switch camera angles. Okay, first we're going to power up the NeoPixel strip itself by turning on the power supply. Of course, this doesn't do anything because it has received no commands yet, so it's just going to sit there blank. And now we're going to turn on the Apple II, which will simultaneously power up the Arduino. And as you can see, the colors go into a default mode. Now we're going to boot up and go into my NeoPixel program. And here are the different options that I have programmed into the NeoPixel system. First is the Step 2 Next mode. All of this does is it toggles the interrupt pin, and every time you press 1, as indicated here, it just steps to the next version. So if I hit 1 again, it'll go to Fade Color mode. 1 again, it goes to Twinkle mode. 1 again, goes to Static Colors. And 1 again, it goes to Chase mode again. Now, we can also pick specific modes that we want to show. Say we just want to go straight to Twinkle. We can hit 5, and it goes into Twinkle mode. So let's say I want to go to Color Fade. That is option 4. And now it's directly in Fade mode. So let's go back to the static mode by pressing 2. With these built-in commands sent over the Gameport connector, I can set this to any of those defined Apple color modes I want. But that's not all that it's programmed to do. As you can see with these other commands here, we can tell it to fill the strip, or fill a section of the strip with a specific color, set specific pixels, then tell it to do one of the 2 animations. So let's go ahead and do that. Let's fill the strip with let's clear the strip entirely. So if we go to 6 and I put in all zeros, start at 0 and the end is 60. Now the strip is off. Now I can send it whatever color I want. Say, let's do fill strip. Let's make it that red and no green, and we'll give it a little bit of blue so it'll be kind of purpley. We'll say the start is 0, which is the beginning of the strip, and we're going to give it 30 pixels, so that it's only going to have 30 of the lights lit. We do that, and as you can see, this half of the strip is set with pink, and this half is empty. Let's set the other half. Let's do fill strip again. We'll make it no red. We'll make it all green. We'll make it a little bit blue. Start is going to be 30, and the count is 30. If I did that correctly, it'll color from right here. Yes. So now it's a weird, lurid mix of pink and teal. Now, let's say we want this strip to chase. All we have to do is select 8, and the strip chases around whatever we've programmed it to chase. Now let's say we want the strip to fade. All we would have to do is tell it 9, and the strip will fade whatever is already in the strip. When we're done, we can just hit 2 to go back to Apple Colors, or we can exit, and it will keep doing what it was doing. So, for example, let's tell it to fade. We'll tell it 4 to fade, and if I cancel out of this program, I can do whatever I want, and you can see that the Arduino controller continues to make the system change color. Now let's go back to the installation to give you an idea of how I think that the strip should be installed when you finally get your own transparent Apple IIe case. Taking a look at the inside of the chassis here, I believe that installation of the strip right along the front of the keyboard here is going to give you the best result. That should clear all of the mounting screws perfectly. I've tested this with a dry fit with a plain case, and it seems to go together just fine, although you can't see the LEDs in that case. Along this side, you can run the strip right up along the edge of the motherboard, and it just clears these screw connections here, which means the case should just keep this in place through friction fit alone. On this side, when you install it, you may require a piece of tape right about there on the power supply, right here, to keep the strip back in place because there's extra spacing right here. You can use double-side tape, whatever you want to keep it in there. And as far as the Arduino controller, I found that this spot right in front of the power supply seems to be the best place. It seems to just kind of sit in there really nice between the power supply and the speaker. Of course, you can double-side tape that in place if you want. You could also stick it up here if you like, or shove it down here underneath the keyboard, but wherever it fits your fancy. And of course, no demo would be complete unless we saw it in the dark. Now let's talk about some improvements we could make to the project. I'm driving things using negative logic because it's simpler to wire up and demonstrate. The downside is that the default state of the Gameport pins is negative. That makes the Arduino do weird things right when you turn on the Apple or when you reset the Apple. With some pull-down resistors and trivial changes in code, you can drive it with positive logic instead. This would ensure that when the Apple is reset, the Arduino will keep on doing what it's supposed to do. It's possible to reduce the number of Gameport pins needed by having pins mean different things in different modes. I went with the easiest route and gave each function its own pin. You can also program more animation modes into the Arduino, or add commands to allow you to change chase and fade rates. The sky's the limit. As you can see, tricking out your transparent Apple IIe can be an easy and fun process. All you need is an Arduino, NeoPixel strip, a power supply, some wires, and soldering tools. Now get out there and show your Apple colors. You can get the source code and disk images for this project on my website at jcm-1.com/NeoPixel. Thank you for attending, and remember, Apple II forever! And because you're all awesome, use the following code to get 10% off anything at jcm-1.com. Valid for one purchase of any amount through August 2020.